Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Whose idea was it that we are meeting indoors at this time of the day with that kind of weather outside? It's cold outside. Okay. We're planning the new teaching building at the moment, which you hopefully are still young enough or slow enough in your studies that you will still see it. This will be out of glass, like in outside glass, inside glass. There's wooden floors and glass walls everywhere. Would you see this as a good idea? Say again? You would like to sit in a glass box? Okay. Don't worry about the temperature. They will have blasting Canberra air conditioning, so you have 10 degrees indoors. Don't worry.
Will there be computer labs?
No. No. No computer labs in there. So you're not easily distracted. If you see a whole train station moving past behind me, you will always be fully focused, right? You're not easily distracted by anything.
We can talk about the deadline for the train scheduled.
For example, yeah, we can use this as plenty of examples and input. Okay, so you're not easily distracted by anything that moves in the... Are you human? Because if I make anything spontaneously hop in that corner of the room, you will all look there. You will even have a hard time to suppress looking there if I announce it. Why is that?
Well, hang on, you said trains. What trains?
Because you belong to this tribe which was not eaten by the tiger. You actually responded when something moved in the corner of your eyes. That was a few 10,000 years ago. And that's in your brain today. And you can focus as hard as you want, and you can concentrate as hard as you want. You will still turn your head. Because this is exactly what made your ancestors produce you. And you're not wiping this away in a few hours, years of concentration. So there is an issue of that people cannot avoid to be distracted to a certain degree. Particularly if you have actually screens on glass walls to the outside, to the inside. If you look at things and all around it, you have movement. But transparency of teaching. Right?
Transparency doesn't literally mean the walls are transparent.
You don't get this metaphor. You have to go a little bit more with it. Okay. This will be mostly, no, at the moment it will be all flat, but that is still a little bit under discussion at the moment. What is already clear is 90% of the rooms will be all flat in there, and they will all be rather small. We're talking 30 to 60 seat places, one 120 seat place, and nothing larger besides one gigantic area, which is currently under definition what to do with that exactly. So this is not yet a replacement for all the lecture theaters which have been coming down. We are not having large rooms to directly replace for that one. But we'll have a theater, and we will have cinemas, or one cinema. And this will be the large spaces. Whether they will be lending themselves to teaching will be a different story. And I hope you all will be able to enjoy that eventually, because this will come online sometime 2019, if you're lucky. Until then, we can enjoy ourselves in rooms like this here. By the way, for your entertainment, I actually very strongly pushed for this room, because this is one of the nicer rooms, I think, which we have. It is much more flat than the others, but it is still inclined in the way that you have a chance to see stuff. And I feel quite comfortable teaching in this kind of environment? I don't know. Do you have any opinion on your different teaching places? What is your favorite place to learn on campus? Do you have a favorite theater? Manning Clark.
ANU Bar was pretty good.
ANU what?
ANU Bar was pretty good.
Okay. How many classes do you have at the ANU Bar?
Lessons we learned.
Oh, it's just lessons to learn. Okay. All right. For your well-being otherwise at the moment, I'm sure you enjoy the beautiful stacking up of all the assignment deadlines at the same time and all the unpleasant deadlines and unwelcome deadlines which are storming at you at the moment. We do coordinate that a little, as much as we can.
Also, it's on purpose.
We try to stretch it out. But there is just a natural progression over 12 weeks that by the end of the 12 weeks, you finally can do stuff. And of course, lots of your assignments are just accumulating there. And there's also no ban on deadlines and things happening in last week. That was last year still the case, that you couldn't do anything, you couldn't have any deadlines in week 13. Now you don't have week 13, and that regulation doesn't exist anymore. So you can have a deadline on the very last day of teaching. And some courses will do that. Okay. Any feedback for us, me, at the moment? You're reasonably happy? Or you're naturally unhappy, that doesn't... Okay, anybody who is reasonably unhappy who is naturally happy? Oh, you have naturally happy people.
Is happiness the default? Or is it something you attain?
Now, you're coming from a European perspective. You have seen this negative connotation. This, if somebody is naturally happy, it doesn't mean he is naturally stoned or something. It's not the same thing. So having a naturally friendly, open atmosphere is not necessarily a negative thing. I know if I land in Frankfurt, getting out of the plane, and I still have my Japanese or Australian attitude to it, and approach the first guy at the counter with my Australian way of opening it, he thinks I'm completely nuts. I must have lost my marbles way back. I was just, why is this guy smiling at me? He's just looking at me really intimidating. And it takes me always a few minutes to go, yeah, sure, okay, let's talk shop here. And then beginning to take you serious more. So if you think about this kind of happy is suspicious, yeah.
Russians, so we have the same thing.
Yeah. Or, I mean, talk about people in Denmark. There isn't even a word for please. So that doesn't really sink in. Talking about our course and lots of happiness. How are you doing with your assignment 2? In order to help you a little bit and support you for assignment 2, I changed the order of the stuff here in the lectures a little bit. And I would like to talk to you about distributed network stuff first, so that you have a little bit more background to get your assignment 2 solved. Okay? So where did we stop last time? Last time, we tried to fail or analyze failure. Those are the different possibilities how you can categorize your system in terms of failure resistance. Failing in the time domain, not a big topic for you at the moment. Failing in the value domain, fail never, this is your domain which you're usually programming in. Or fail uncontrolled, something just exploded and I have no idea what's going on. This is usually the distinguishment. Then we have all the methods, some of them you're familiar with, to avoid failures, deadlock prevention, deadlock detection, any form of program verification you have seen so far in your life. You try to make your system robust, perfect, never failing. Right? Now, if you have done your maths and you have proven that your system can never fail, you're leaning back and you call it a day. I have proven that. Here's the math. Trust me on that. Are you that confident? No, you're not. So this is what happens in real life. Fault prevention, avoidance, removal. Yes, we have all these methods, and we do that, and we apply that. And then after we have done all of that, then we talk about fault tolerance. Because we know that practical system, regardless how much verification you throw at it, will in many cases, maybe in most cases, maybe in all cases, will eventually have the possibility still to fail on you. What do you do then? You provide fault tolerance. What does fault tolerance mean? Well, it fell over, I don't care. I'm a tolerant man. What does fault tolerance mean? Any idea? If I asked you to give me a fault-tolerant system, what are you thinking?
Can identify that some part of which is wrong and correct it?
Speak again in a full sentence.
It can identify that some part of it is wrong and correct it?
Yeah. It can identify that some parts are wrong and correct for them. What do you mean by correct for them? How do you correct for a system?
Essentially make sure that you don't further violate conditions. Maybe drop the result.
Yeah, but why wouldn't you have done this while you have been writing your program in the first place?
You write modulus systems, and one module might fail, but you
The other guy's module failed, mine is good.
might be one module.
Yeah, okay. Okay. So you're on the right track. You need to have a mechanism to detect that your system has produced a fault. How would that materialize? How do you detect that your system is currently in a faulty state?
If you're implementing an algorithm, it might be triggered to verify the results are correct. So you can have some assertions.
Assertions. Okay. Or as you learned in the past, you could formulate contracts all around your system. So every time you leave a specific module, you leave a specific function, you do some post-condition checking so that if everything is still honky-dory, then this predicate has to hold true. So you have assertions, post-conditions, contracts, which all are by default always true if your system is running as you expect it to do. So it could be a tautology. It could be you're proving things which are obviously true, and you can never get out of this one. Besides, there's something you haven't thought of. Or besides, your hardware feels a bit on the wobbly side today. Huh? Exactly. And what you're doing then? You just detected that your system is in a faulty state. For example, you have a state machine which transitions happily one state to the other, and all of a sudden you detect that your state machine is in a state which isn't even defined, which doesn't exist. Roll back to a known state? Yeah, okay. Okay. Let me suggest a few things. Those are the technical definitions of what you can do. There's something like full fault tolerance. Full fault tolerance means that anytime something goes bad, you replace it with some module which is still good. This is the philosophy of I have lots of spare resources. I have 5 other computers hot running, standby. in case anything goes bad. Your system feels wobbly today. You don't fuss around. You just rip out the cable, plug in the next machine, keep that thing running. You just throw resources at your system. This can be now on a software level, can be on a hardware level. You have redundancy in your system. You can switch over immediately to another system without any loss of functionality observable for the user. That's a pretty high goal to have. Can you do something like that? Is that even thinkable? That you can switch over to another system and nothing ever happened. You know, not ever observing anything.
Yeah, because separations make an indentation.
Well, that's the way how to design the whole thing, yeah. But just from a hardware perspective, can you imagine a system which can do that?
What happens if you run out and you use all 5 computers?
Yeah, that's one of the insights which always goes with full fault tolerance. Full fault tolerance can only handle with a limited number of faults. So full fault tolerant always need to have the attribute, I'm full fault tolerant for 5 major flaws. After that, I'm running out of stuff. So it's exactly the right observation. Full fault tolerant cannot be upheld infinitely. At some point, you're running out of stuff to replace and to throw into the equation. So there is no such thing as infinitely running full fault tolerant. But my question was different. My question was, can you implement a system which there is an explosion somewhere? One of your CPUs feels like it needs to leave a crater on your board, or melts slobbery over your PCB. Can you handle a situation like that? Can you design a system which can still live through that? Do you know a system which can do that?
Presumably flight controls.
Yeah, you all have been using these kind of systems. If you ever have been entering an airplane or any other dangerous, fast-moving system, they are all designed like that. You can, I'm not recommending that, but you can take an X, if you manage to get this X into the cabin, and can smash away at the flight computer, at any of the flight computers on board of your aircraft. It will not even jerk. So yes, you can design systems where you can physically destroy a part of the system, and the system is not responding in any unexpected way. It's flying continuously and smoothly further on. It may not be that smooth for you with your axe in your hand in the middle of the cabin after that, but the flight will continue smoothly. So yes, you can do that. You can implement something like that. Can you implement that for communication systems? Can you design a network which does that? Well, your assignment is asking for that a little bit. So what happens if in your network someplace I go and rip out an Ethernet cable somewhere in the middle of it? Well, that's the definition of internet. That's the very definition of how the internet works. You rip out the cable anywhere, the routers around it will detect that situation and route the packets around it.
Unless there's one cable to the outside world and it's controlled by that.
There will always be firewalls, bottlenecks, and other situations which will make this a bit harder, but the general principle still applies. Now, if you think about the internet, this is not necessarily working without any kind of noticeable delay for the user. If you look really, really sharp, you will notice a few milliseconds which you are losing in that process. Could you design a network which does not lose a beat, does not lose a single bit if you rip out a cable in the middle of it? You can't?
You can't. That's why you have some other protocols to ensure that it's completely different instead of just divided
Okay, where would you need something like this? You rip out a cable somewhere, not even a single beat is missing anywhere. Say again? Loading a video, not necessarily, because your video is actually buffered. So for your home, for consumer level video streaming, there is a quite significant buffer between you seeing something on the screen and what comes into the internet, what comes through your network port. So you have to be just fast enough that your buffer is not running empty in the time in between. But you're not actually watching anything live in digital TV. There's always a buffer in between.
It's like service, I suppose.
Yeah. Or again, the flight controller. Of course, you need to have communication between all your sensors and your flight controllers, and you don't want to, well, wait, I have to reconfigure my network. Just everybody holds their ailerons in the right position at the moment, and we will be coming back. Yeah, now I'm coming back. You, of course, want to keep this continuously going, and you can do that. We are doing that. You can actually design networks where there is not a single bit jittering when you reconfigure the network.
Well, you effectively resend some part of it.
No, you can do this redundantly. If you have the resources anyway, you can actually send the same information through multiple channels at the same time already. This is very different from the internet.
But machine have a very dense network.
You need to have enough capacity for that one. But it's not that you have spare wires lying around not doing anything and jumping in when something is cut somewhere else, but you're utilizing all of your networks always. So you have information flowing through many channels through your network concurrently. And that, if you do it right, enables you to cut some of them without any noticeable change in the actual communication flow. Quite cool. Graceful degradation, what does that mean? It means that you're reducing some functionality of your system while keeping the vital functionality of your system, the essential parts, alive. So for example, if an APU, a power unit in your airplane is going down, you will usually reduce functionality somewhere. For example, power down your board entertainment system, which is pretty power hungry. But you won't power down your flight controllers. So you can always reduce your system a little bit. That's called graceful degradation, as opposed to random degradation. If I just lose stuff somewhere, and then anything can go bad, a graceful degrading system means that I can do damage to it, and it will fall back to a basic functionality state. And you can also iterate that a number of times until you come back to the bare bone functionality where you say, okay, one more fault and I'm actually out. And fail-safe is an often confused term. Fail-safe means the opposite of what most people think it means. Fail-safe means you're not safe of failures. It means that if you fail, your system stops, but in a consistent and safe way. Obviously, that's not the preferred way for a flight controller, but it's the preferred way for many other systems. Like, for example, large databases, where say at some point, I want to shut down the service, but I want to shut it down in a controlled way. That's a fail-safe system. And that's the last form of fault tolerance we have here. Okay. So that was...
Can you combine all of the fault tolerance methods? Like,
Yeah.
let's say if you run out of computers.
Yeah.
Or,
Basically, you can have all of them at the same time.
yeah.
You said that as long as I have enough resources, I have a fault-tolerant system, full fault-tolerant system. When I run out of crucial resources, I go down to a fault-tolerant, graceful degrading system. And even if I run out of those resources, at least I have a fail-stop, which is still safely defined. Yes, so you can have all three of them in one system. That's true. I think we are in the binary phase of going through towards Antarctica again. It's definitely warmer outside. Okay. Any further questions about safety and liveness, fairness? At the moment. So, big chapter, distributed system. That's actually the largest chapter of this course. And I start this by repeating things which you should know. Network reference model, OSI model. I would assume that more than half of you have seen that in the past.
No.
You have not?
It's first year.
Okay. Okay. There will also be a few who have never seen that in the past. Who has seen the OSI model? Oh, okay. That's a bit of a surprise. That's not exactly half. That was more like 3. I have more than 6 people here. So that's interesting. Okay. Then good thing we are repeating that. What does it mean? The 7-layer OSI model is a common network definition protocol, which is in this form, which we were presenting here, hardly ever used. Why do I present something to you which seems to be utterly impractical? Because close to no industrial protocol is implementing that. Is that just because lecturers like old textbooks? And
Because you can categorize implementations as implementing sample noise.
Yeah.
You want to describe the abstraction by the protocol.
yes, because the OSI model is the language of network protocols and network definitions. So whatever network protocol you're actually defining, you will always refer back to the OSI model. And what I'm doing here, this model implements level 2 and 3 of the OSI model. And everybody knows what you're talking about. It doesn't mean that your system has exactly 7 layers, but it means that everything you do in your system, and you will be able to map everything what you're doing in your system to the OSI model in a fairly straightforward way. So, it actually says so pretty much on the slides. This is a graphical representation of the OSI network model. I have 7 layers, and let me just quickly go through what that means. The basic idea of a layered network model means that you have a user which communicates, your task, your high-level task, which communicates with the top level of this OSI model. And then you trickle down layer by layer until you come to the physical layer. The physical layer actually talks about cables and copper and fiber wire and can communicate your information. But before you get there, you will trickle down to all the layers of your network protocol. Every time you go to a new layer, you usually will have a new package, a new wrapping around your piece of data. There will be maybe a new header piece of information, maybe a new tail end attached to your package, and it's just wrapped in some more information which tells the postie, which is responsible for this specific layer, what to do with it, what's in there, how it's encrypted, or any other thing which is responsible, which this layer signs responsible for. Okay? It's funny how we are slowly looking more like a course giving on an ice shelf in Antarctica someplace. Just like that, yeah. I can't do anything about it. The thing is fully automatic. So far so obvious. What does the physical layer define? This could be, for example, the Ethernet cable and the amplifiers around it, the physical amplifiers. the physical connectors, or the fiber wire connectors which you have around it. The physical layer is usually reasonably easy to understand if you come from an engineering point of view. There's no such thing as bytes on the physical layer. At least mostly it isn't. You can define something like that, but mostly it isn't. Mostly it's just a single cable and the way how you can operate on that single cable. Things which are defined here on the physical layer is, for example, is it possible to access this physical cable with multiple devices at the same time? Or do you have to ask for permission? No, you don't? You don't ask much for permission, do you? Okay. Have you ever heard of the concept of a short circuit? So if you have multiple devices and a copper piece of cable, and all of these devices are putting current, putting actual load onto that cable from different ends, what's going to happen?
Really high currents, potentials.
Briefly, very high currents, and then you hear this famous.
You build the systems to be reliable, so
Yeah, yeah. If the physical layer defines that. If the physical layer tells you, fingers off, if you do that, it will be smelly afterwards. Right? So that's part of the physical definition. And I will show you some examples later where, yes, you will just burn stuff down if you don't look for that. You can ask for forgiveness with your smoldering piece of hardware. Can I have another one? Yeah, sure. Okay. Of course, we know that computer scientists don't necessarily understand the concept of burning stuff down. So from the engineering point of view, most network connectors, and you are right from that perspective, most network connectors which you have today are fairly short circuit resistant, and you really have to put quite hard stunts to burn these things down today. And to make it even more resistant, even if you short circuit stuff, even if the current goes through the roof someplace, these systems are also temperature protected. So you have multiple levels of security for these network hardware interfaces today. So even if you really pump energy in the wrong direction, at some point they will detect that my network driver at the moment has just been peaking beyond 150 degrees Celsius, which is not normal. And it will actually electrically power itself off to prevent itself from doing that. Many of your systems will actually be hardware configured like that. Okay. Otherwise, that's not the level which you as computer scientists are usually working on. But you should have some awareness that somebody has to define that. And you have to know what the cable is capable of, what you're pulling off. I will give you examples for the physical layer later. Now, this is where computer science is actually going a little bit more into charge. It's the level where it's transitioning between engineering and computer science. Data link layer. What does the data link layer do? Data link layer gives you basic flow control between endpoints. This has nothing to do yet with any internet packets or anything like that. It gives you a possibility to transmit bits from one side to the other and to have a speed regulated form of transfer. Something goes bad in the process, you can slow things down, you can give it a green light again if the other device can receive data again. So you can have a little bit of flow control. You define how my data is encoded, what kind of signals do I give into this one, do I have error correction possibilities. So if I have a big fat magnet lying on my cable, I have a motor lying on my cable somewhere, and the electromagnetic interference of my cable is significant. This is the layer which usually saves it. if the physical layer is not saving it. So you can protect yourself on the physical layer against this one, or you can protect yourself on the logical level on that one. As computer scientists, what are you doing to protect yourself on a network cable against bits which are going, wah?
Wrap it in aluminum foil.
You wrap the bits in aluminium foil.
No, the whole cable.
At the cable? Yeah, then I come with a bigger motor. More aluminium foil. Okay, I see. Okay, just hypothetically, you're running out of aluminium foil.
He sounds a lot like an engineer, doesn't he? Filthy engineer.
Yeah. So what do you do on the next level if you actually have lost a bit? For example, if your connectors are wobbly. Any idea? Come on, you're a computer scientist. Give me any idea. How do you protect yourself against bit falling over?
Can you add a few extra bits to tell you whether you change bits?
Redundancy. You add a few extra bits. How do you do that? You have a backup bit for every bit, and every time the first bit falls over, you take the backup bit.
It's too much overhead.
Some sort of like, I guess you can just check whether it has changed. Oh, I know someone was showing me a few examples. I'm sure there's just like,
Uh-huh.
of just like little algorithms you can do to guarantee that.
Little algorithms.
Well, like,
Yeah.
This lovely thing called the Hamming code.
There's a lovely thing called the Hamming code. Who has heard of the Hamming code? What is a Hamming code? Shit, now I put my hand up now.
It's like a Venn diagram thing.
No? Yeah?
Have a number of check bits and depending on
No, what's the basic idea of a Hamming encoding? What's the basic idea of a Hamming encoding? So there's also the notion of the so-called Hamming distance. What is the Hamming distance?
Like how many bits you check over before you have like is it a parity bit? I can't remember what that's like.
Could be. But the general notion of a Hamming distance in your code means that how much interference can I have, how much can my code change so that I fall again into a valid code. So you have codes which are valid. They're representing bytes, words, certain structures. And between those valid codes, there's a certain number of codes which are invalid. So when I change, for example, a single bit somewhere, usually in a Hamming code environment, if I change a single bit somewhere, the whole idea of a Hamming encoding is that by changing a single bit, I will almost certainly, or if somewhat decently, I will certainly fall into a code which is not valid. So I detect that.
Is it equivalent to saying that any word in your language is encoded by like multiple like representations?
You can think of it like that. Usually people think in terms of there are certain codes which are valid. If you enumerate all of your possibilities in flipping all the bits, some of them are valid. Now if you move a little bit in one direction and you're not moving far enough that you get close enough to the other one, you know that I'm a little bit away from this valid code, but the distance to this valid code is shorter than the distance to this valid code. And that means you can do a nice trick. You can say I'm closer to this valid code, so that means I detected a single bit error, and I know that I can move to this valid code back, so I can correct my code back to a valid state. And the longer, the larger your Hamming distance are, the more resistant are you to individual bit errors. Because then if you have a gigantic distance between two valid codes, many bits can fall over until you actually reach the other code, or you get close enough to the other code that your Hamming system will change to the wrong code. And still it can detect that there was a problem, even if it's correcting to the wrong code. This is all stuff which is done here. Yeah?
It could be halfway between codes, and then you know that there is an error, which way it's.
Yeah. Often you have a Hamming code which is widely used is a Hamming code which can correct single bit errors and will detect double bit errors. So with a double bit error, you're ending right in the middle between two valid codes, and you don't know what to do, but you can flag that something is dodgy. With a single bit error, you can also flag there was a single bit error, but I can still fall to the valid code. I can actually correct that. That's the most widely used Hamming encoding. So you have to make a guess how likely it is, how many bits per transmission can actually fall over in your system. This, by the way, does not only apply to network communication, this applies also to your memory. Because your bits in your memory, you have so many of them, will occasionally fall over as well, and you want to correct that as well. Okay. HDLC, LAPVD, LLC, lots of different fancy words to describe currently defined data link layers. As you said, synchronization, flow control. You can have traffic lights at both ends of your network that you can indicate that please start sending, stop sending. I'm still busy processing the previous one, so slow down a bit. So you can say again?
Turn on red LED means a constant.
Exactly. Soldering LEDs onto your network cable, that this is a bit obvious. Yeah, exactly. So next important one is the layer which you are implementing in your assignment, called the network layer. What's the network layer do? The network layer is the first layer which is not thinking in terms of point-to-point connections between two devices. The network layer is able to switch your packets into the right direction, connect to the port which leads in the right direction of your overall network. This is what is then called routing. And examples for that, X22 or IP, the Internet Protocol. That's a classical example for an implementation of a network layer. Yeah?
Sigma is level 3 by this definition, right?
Say again?
Sigma first
Yes.
definition was level 3.
Yes.
It's shown everywhere as level 2, which is what's really unique.
Yes. Yes. Yeah. Well, it involves both aspects. But it also involves the network layer. Okay. If you look at this diagram on the right, I have communication going from the left to the right. And there's a middle element. There are a number of nodes through which this is going. And the node in the middle is only living up to the network layer. The node in the middle doesn't have any higher levels implemented. Why does that make sense? And how would you name this if you want to buy this middle node in the shop? Okay. This is the piece of hardware which you buy in the shop if you ask for a router. Then you get a device which implements the first 3 levels of the OSI model, including switching to different output ports, which makes it an actual router. Do you have other devices where you can plug multiple devices into, but it's not a router?
Switch and hub.
Router, switch, hub, lots of fancy terms. Anybody is able to define what that means? Router, switch, hub?
Whatever the manufacturer says it is, man.
What's a common notion of a switch? There is actually not a noticeable difference between a switch and a router, and some manufacturers are calling these things switches, others are calling them router. It depends a little bit how many protocols you speak. If you buy a big 19-inch board which you plug into a big rack someplace, they're usually called routers. If you buy a little device from Harvey Norman which you put underneath your desk someplace with 4 ports in it, they're usually selling this thing as a switch. But functionality is pretty much the same. So from an OSI definition, there is no difference between a router and a switch. It is more how many protocols can it do, how fast can it do it, things like that. What's a hub? Yeah, okay.
You have a MAC and IP address. It's like two different routing systems.
MACs have nothing to do with routers. That's it. We'll talk about MAC layers later on when I talk about Ethernet protocol. Okay. What's a hub? Anybody bought a hub in your life before?
I have a USB hub.
You have a USB hub. What's a USB hub doing? No. No.
Yeah, combining inputs.
No. A USB hub is not actually routing. A USB hub is just electrically connecting all of this stuff into one. Pretty much. Yeah, there is some stuff in between to make it stop blowing up, yeah. But logically, it just connects all your cables into one.
And it's up to the individual devices to not trip over each other.
And electrically decouples them to not short circuit all the time. Yeah. But it's more often electrically coupling, not a logical one. The hub is not making a decision when you have a USB package coming in, where do I send that to? So the term hub is actually correctly used in that one. Do you also have something like a hub for Ethernet? For network cables? Is there something like an Ethernet hub?
Ethernet defines the ability to do so, but no one actually does.
Yeah. You are too young to know that. Ethernet hub went out of fashion a few years ago, but an Ethernet hub was basically a physical repeater. You plug the cable in on one side, and this signal was physically repeated on all cables which are going out of that. This is a hub. Now, a hub is, of course, a lot cheaper than producing a switch, because a switch needs to have the network layer implemented there. There's lots of logic which need to happen there. You cannot just do this electrically by amplifying signals. But what is the implication if you have a hub in your system? What does it mean for your network?
It's sort of strangely like asymmetrical. Like have low signal, it's the same signal going out, but then when it comes back, it's like combining it. Or
Yeah. What does it mean for the throughput of your system? Okay, let me ask the other way around. You buy a new computer, and it has, if it's a desktop machine, it has 25 USB ports. Why does it have this gazillion of USB ports? If I could just use one USB port and have a hub on my desk, which connects all the other USB devices, wouldn't that be much more convenient? You get the point why a hub is actually a problem in terms of performance. The moment you have a hub in your system, it just means that everything is one big cable in a logical sense. So every device which plays on any of the cables which are connected to your hub, this signal will be visible everywhere.
Aren't most computers putting all the ports into a hub anyway?
Well, then you got a cheapskate version, yeah. Then they cheated on you a little bit. But the idea is if you have these 25 USB ports, of course, you don't have a hub in your computer. But you actually have different USB host devices in your computer, which are physically and electrically different and can be pumped with data from your computer side completely independently. Otherwise, there wouldn't be any point why you have 25 USB ports in this thing.
Still only have the one CPU.
Yeah, but your CPU is a lot faster than the throughput what you get through a USB port. So your CPU is easily able to pump through 5 of your USB ports in sequence. But if you do this only, if this all goes through a hub, and you pump information through one of your USB ports, that means all of your other devices are not able to do anything at the moment either. Right? So you need to be able to exploit the fact that your CPU is usually one order of magnitude faster then all the USB devices, or maybe even 2 or 3 orders of magnitude faster. I mean, I don't know how fast your mouse is. Well, if you have a gaming mouse, actually, some of them are pretty fast. But in general, USB devices are pretty slow. USB devices connected through General Hub. Lots of issues with that. I still remember the time when you had something like disk burners connected through USB devices. There's also no protocol defined on USB 1. Everybody has done basically what they wanted. USB 1 was basically a definition of an electrical plug and a general philosophical fluffy definition of what you can do there. So every manufacturer has done what they wanted there. And it also means that every time any of the devices got out of sync and didn't quite know what to do, what they classically have done over their USB drivers was pressing reset. So any device which gets a little bit worried just presses reset on the USB bus, which means all the other devices which are connected to the same hub also goes wing, which if you just burn an optical drive at the moment, optical disk at the moment, it's kind of annoying if your mouse driver just presses reset all the time. But that was due to the time when USB was utterly undefined. It's not perfectly defined today either, but I think we made a little bit of progress between USB 1 and USB 3 by now. Talking about network devices, we're going back to Sahara mode, I like that. Have you now some comprehension between switches, routers, hubs? Yeah, okay. You know what to ask for if you want to have a device which has these 3 green boxes inside somewhere when you go shopping next time. So the next layers are only existing on your endpoint devices. They're only existing in your actual computers which you connect to a network. Next one is the transport layer. And transport layer is for example, responsible to establish a standing connection between endpoints. You want to open a channel between devices where you can then hand data through. The management of this channel, opening this, producing data flow information between the endpoints of your channel, this is the responsibility for the transportation layer. For those who have been playing with internet, this is where TCP is defined, or UDP is defined. This is a layer where you establish connections between endpoints. Okay. Then you have a session layer. The session layer is responsible to communicate sessions between full applications. This is one abstraction level up. A full remote procedure call between 2 machines is usually defined on the session layer. How do you call an operation, a method, on another machine? It's not sufficient to just have a transport layer for that, which would be TCP, for example. You would need to have some additional information about data types, protocols, handshaking, which are understood by your programming language, by your runtime environment, to hand this information over. This is the session layer which you have there. Then a layer which is often, or has been historically often, forgotten. Basically because the internet and many other protocols have been designed somewhere in America. So who doesn't speak English? Presentation layer. You need to have a definition somewhere. What is my encoding? In what kind of character code, what kind of encoding am I communicating my information to something else? Now this has become standard today, luckily. And we are, for example, communicating in all of your emails, on your communication to anybody else. Pretty much anything you can connect to your system today will understand ISO encoding. That's another layer of encoding which is between your applications and the individual network layers underneath that one. And today, there are very, very few languages which are not part of the ISO encoding standard today. Actually, I think the very last widely used languages have been standardized a few years back. You find ISO definitions for the last languages, Sinhalese, into the ISO standard today. Anybody would be aware of any written language which is not part of the ISO standard today? And it wiped away hundreds and hundreds of national encoding standards which have been living for a long time. There are, for example, still remains of Japanese encoding standards which have been surviving for a long time. And they're also replaced by ISO encoding quite widely today. Your web browser will still understand the traditional Japanese encodings, by the way. So there are still a few exceptions there, but ISO encoding is capturing all of that. Nice. Having some awareness of this.
Will something like RPC level 6 above it as well?
RPC, you can decouple that. You can have a presentation layer on top of an RPC. Right? Or, for example, your encryption layers. If you use PGP, like I'm using, if you ever receive an email from me, you usually have some kind of a note that you don't have a PGP address, so the best thing I can do is I can sign it for you, but I cannot decrypt it for you. I'm not doing any of that manually. I'm just defining, hello?
Sorry, I lost it.
Okay, sure. I'm not doing any of this manually. This is just another layer in the network protocol, and you can splice in another layer for encryption into your protocol so that your email client, for example, will never know about this. The form how I do, for example, PGP encryption or any other encryption on my system, my email client has no awareness of this. For my email client, I'm pumping clear text information in and getting clear text information out.
Well, it depends.
What do you mean it depends?
If you mail clients now, we need to download the raw source and encrypt it manually.
If my what?
If you have a stupid email client like what Mac app,
And then?
like the standard mail client of Mac, like you want
I'm just explaining, listen please, I'm just explaining that your mail client has absolutely no knowledge about this because this is a network layer. So it really doesn't matter whether you have a stupid, clever, expensive, free mail client. You're sending a mail from the perspective of your mail client through an SMTP server from the same interface, and on the network layers underneath of that, the encryption is being done with complete ignorance from the perspective of email clients.
depends how you follow this.
I explained to you that doesn't depend how you implement that. That depends whether it's a network layer or it's part of your email client. You have email client plugins, right? And many of you are using plugins to do the same thing, or you can make it part of your network stack. If you make it part of your network stack, then it doesn't matter what you use on top of that. That's the beauty of a clean network interface. I will give you examples later. When you have a clean network interface, you can change everything above it without any kind of change for the rest of your system. You can keep a certain interface as long as this is reasonably standardized without changing the rest of your system. That's the point of having a layered system. So in this case, I can, for example, use the network layer and put another transport layer on top of it. I will show you examples how this is being done. So you can use your routers for TCP/IP or for other protocols. As long as you keep the same interface, the same definition, it doesn't matter. That's the whole point of having a layered system. And this is also one of the reasons why, if you have a layered system, you usually want to have not 25 different layers, because with every layer you have a further step of handing over data, of encryption, encapsulating, putting packet information around it, and that may slow your system down. Otherwise, you would define your operating system, your networks, all in very fine-grained layers all the time, because layer technology enables you to have clean standards and to exchange different layers later for the price of a slightly less efficient system. One of the reasons why many industrial standards have fewer layers, because they focus on the few layers where they need this functionality and combine, say again? 5 layers. For example, you have often a data link and a physical layer somewhat collapsed into one layer, because many network protocols do not want to have the luxury of being able to exchange the physical medium underneath it. So you don't splice in an additional layer between data link and physical, because you don't have the intention of ever changing your cable. Now, luckily, Ethernet and many other protocols have not done that. They have an intermediate layer in between. Otherwise, you would have a very hard time to change to different physical modality. The Internet protocol today, going over what you call Ethernet today, is physically a completely different system than what it used to be in the 80s or 90s. How many physical cables do you plug in today if you plug in your Ethernet port? Do you know that? 8 cables. 8 different physical wires which you plug in simultaneously with your Ethernet plug today. This is a very different physical interface than what you had originally. How many wires did you have for Ethernet originally? Anybody remembers that? Knows that? For Ethernet? 1. And a shielding. That was the original Ethernet definition, and it went through many different iterations. And without that ability to separate the physical layers, we would not have gigabit Ethernet today, but we still would have had 1 megabit original Ethernet definition, because that was the physical limit what you could pump through that system. Okay. So this is just a trick to understand that this layering gives you plenty of possibilities to be flexible later on and exchange some of these layers. That's the point of it. The last layer, okay, this is then the application, a bit of probably the most fluffy defined one. Anything which works on top of that, your actual application, your mail client, whatever it is, that's the application layer on top of the whole thing. SSH, SCP, anything you do from your command line. This little program, which is called SSH or SCP, that's what is happening on your application level. Okay. I think I actually need to give you an example straight away how you can map these protocols. Let's go there straight away. This is how TCP/IP maps onto the OSI levels. You see that they put the lines a little different from the OSI level, but one point will always be identical. This is the handover point at the top of IP, which is identical to the network layer in the OSI model. There's very little possibility to do this in any other way. You will always need to have a handover point between the network layer and the layer which is on top of the network layer. Transport and application is somewhat smudged together, and TCP/IP by itself does not define a lot of presentation. This is just left to, this is what you do on top of the whole thing. Okay. So, let me introduce another protocol which has been slavishly following the OSI model. Of course, you're also too young to actually know about this. This protocol is AppleTalk, and the reason why it's here is because this was one of the protocols which has been following OSI just by the letter. What possibilities did that provide? You have the network layer and the data link and physical layer are completely separated. And that meant from the get-go, without any fussing about, you could exchange the physical connectivity of AppleTalk without any further reconfiguration at all. And that led to the situation that AppleTalk was working over what called itself local talk. That was basically a phone line. That was a twisted pair phone line with abysmally slow communication speeds, but cheap as. You could just use any phone cable from your local hardware shop to build up your network with that one, and you can just plug that one in. Or you have token ring connectivity. You have enough money to build up an actual token ring, physical hardware, very different connectors, much faster, very different protocol to be run on the hardware level to do that. But as the separation between the network layer and the data link and the physical layer was that clean, you could have in the same machine connectors and ports to all of these physical entities side by side without noticing from your user perspective that this communication goes through a port like this and another communication goes through a completely different physical entity. Which also linked to FTDI, fiber cable communication. Again, a very different order of magnitude of speed, or to classical Ethernet access. Yeah. Yeah. No, it's just the name which is used. The name network layer in TCP/IP is usually referring to something below the IP layer.
Even though IP is what handles routing.
Yes. Yes. Well, it's just you have to be careful when you read names in different manufacturer environments. That's similar to when you read the name of switches, routers. This just depends on the manufacturer. If you have your OSI model, you can always, this is just like the network layer in OSI, right? And your manufacturer, yeah, that's exactly what that means. Independent of the local choice. Okay? So, now, this was all introduced before IP. Now, as you know, IP got somewhat popular. Can you keep AppleTalk alive if you now have physically an IP network available? You see it. Right? The only thing you do is you place this on top of the IP layer, and nothing else changes. No, this has been done for many years, as a matter of fact, until it just got redundant and nobody was using it anymore. But it has been done for many years in the transition phase, and no, this was actually very common. And many routers which you still buy today, if you buy a Cisco router today, they still run AppleTalk. They understand AppleTalk for that reason. I mean, you will find very, very few devices which natively can speak this today, but your routers can still speak that.
So back to the physical layer, it's hard because the dinosaurs ate the cables, right?
Exactly. Yeah. Okay. So let's talk about network interfaces which are a little bit more simplistic than IP network, just to get you away from the idea that everything is just an Ethernet connection. You have many other network connections on your system. One of the network connections which you have in your system is called SPI. And if you ever have used an SD card, you will have used an SPI protocol because that's SD cards are defined over that.
Is SPI over? Non-SPI?
That's a variation of it. It's just a tiny variation of it. It's an extension of the SPI protocol. Okay. So storing this on your little terabyte SD card thing, or communicating with any kind of little graphical interface, graphical display which you can buy today. You buy for a few bucks your little OLED display which you can use in your systems, and the interface which you get on these little pins which are coming out on the side are more than likely an SPI interface. So it's a very old, very simplistic network interface, but it is used still everywhere. What does this mean? What can SPI do? You can configure SPI in many different ways. If I only have two devices, master-slave SPI interface, I have hardware on both sides, which are shift registers. Sorry, it's not a hardware course, but you are supposed to have seen 2300 before. You know what a shift register is? No. Okay. You know what a register is? No. Don't believe you. You know what a register is? A register is something where you can load data in one go. You can load from memory into a register. A shift register is something where you can load the data into this register by shifting it from one side, bit by bit, into this register until the register is full. Which means you can connect your register to a single bit interface on one side, and you clock your single bit interface with the bits which are shifting into this register. Was that metaphorical enough to understand what this is about? Okay, good. Without drawing any further electrical diagrams how this can be implemented, so I think you can get the metaphorical idea how this works. So the SPI protocol is defined as having shift registers on both sides, and then you have a clock line on top. You have shift registers and a clock line. How can that work? What does a clock line mean for a protocol like that?
Each time you clock, it shifts one bit or the transmit shift register to the receive shift register.
Yeah. So you provide two pieces of information. You provide a bit stream to the other device. So on one of your cables, you're just switching up and down to encode and symbolize the individual bits which are going through your cable. And on the other cable, you say, how fast is that happening? On the other cable, you communicate your clock. The clock changes with every clock cycle. The bits which you pump through the data line only change when you want to change from on to off on your bits, on your bit stream, communicate to the other side. Why has this been so vastly popular, and is still so vastly popular in electronic designs everywhere? You cannot buy a microcontroller today which does not support the SPI interface, which is quite remarkable.